So we're now going to go on to how to solve the KDV numerically, and we're going to learn about this very powerful method, and we're going to start going into this numerical method and understanding it in detail. And the numerical method involves the use of the fast Fourier transform to evaluate the integrals, evaluate the derivatives. Okay, so it's exploiting a few things here. It's exploiting the structure of the fast Fourier transform and the speed of that, and it's got this idea of the split-step method as well. And we're going to use this to solve lots of the equations that follow. And we're going to even try and apply this to the traffic waves, and we're going to see that it works really well for that as well. It can be used to capture the shock and everything, okay, using a smoothing scheme. Okay, so first of all, we've got to start out and understand something about the Fourier transform. First of all, the Fourier transform and the Laplace transform are the same object. They're just looked at from different directions. So much of the properties of and the connections, and it's very useful to have that idea and understanding that they're basically the same thing. Okay, so the Fourier transform, we call it, say, f hat, or I've used this of k, and sometimes they use omega depending on the variable, is the integral from minus infinity to infinity of, this is the standard way of writing it. There's lots and lots of ways of writing it. And then the inverse Fourier transform has this 1 over 2 pi. So really it would be much more logical to have hat of k e to the I k x dx. And you'll find dk. You'll find lots of places where they shift this 2 pi, they put a 2 pi in here, or they try to make them look more similar, because they really are the same transform. The only difference is that this conjugation, so it's the same, it's a unitary transformation, so its inverse is the conjugate, if you like. There's a lot of deep maths behind this. So, the most important property of the Fourier transform is as follows. So we take the Fourier transform of d by dx of f, okay, which is the Fourier transform of f dashed of x, if you like. So we have the integral from minus infinity to infinity of the x derivative of f e to the minus I k x dx. Now we can integrate by parts. So we assume here that there's actually a very strong statement about what it means for this function f, but to be able to be a Fourier transform. But we basically assume that f of x, the easiest way to think about it is that f of x has to go to 0 as x goes to plus and minus infinity. Okay, it's more, you can easily generalize that, okay, and get rid of it and change it. But I'm sure that's very clearly written there. You can easily generalize this to different problems. In fact, strictly speaking, you've got to have this to be true. But it can be generalized to functions that don't. You can have Fourier transforms of functions that grow, like polynomials and things like that. Okay, and it's called, there's a whole theory behind that. All right. So this is the most important property here of the Fourier transform, that we take the, so we integrate by parts. So we get f e to the I k x evaluated between minus infinity to infinity minus, and then we shift the derivative, the integral from minus infinity to infinity of f times Control Z, writing it all out fully. Okay, and this of course evaluates to make 0 because the function vanishes. And then the minus, and then the derivative of this is minus, so we end up with equal to the integral from minus infinity to infinity of I k can come out f of x e to the minus I k x dx, which is equal to I k times f hat. Okay, so this is amazing because it's turned differentiation into multiplication. And one way to think about the Fourier transform is it's a diagonalizing transformation for differentiation. But it turns differentiation into multiplication by IK. And this is there's a few other operators that are also diagonalized by it, like the shift operator, for example. And that's why you've got lots of problems where differential equations leads to things shifting and moving like waves. Okay, you might like to think about what the Fourier transform of the shift is. Okay, what I mean is that what's the Fourier transform of f of x minus a? Okay, that's equal to dot, 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 dot. Right, so the shift operator also becomes multiplication, not by IK, but by something else. Okay, so the key point to the Fourier transform for us is that it's a way of calculating the derivative that's really simple. So what we can do is we can take the function to calculate this derivative, we Fourier transform it, multiply them by IK, and inverse Fourier transform it. And both of those, the Fourier transform can be done really quickly because we've got access to this very powerful algorithm called the fast Fourier transform.